Clean up your mind. I'm so sorry. I should have to enunciate my words better. Hey, we're here. We're welcoming everybody back. This is section 2-1 for PreCalc, and we're going to see what we can do with getting this stuff going. It's information you've done before, but before we get going, because I've got you warmed up the crowd with the jokes that we did, well, we got to get this over. It's not working. Good Lord. Come on. There it is. Polly is the name of the bird. Where's Polly? Right? Polygon, right? It's Friday. it's my class. I decided this is what we're doing. And because we're doing the stuff we're doing, I think you'll like this one. Okay? No, that's Polly. And where is it? There it is. Polynomial. Okay, are you guys starting to figure out why the math department likes me over here? They're like, "Oh, you can't do that. That's not black and white." And I go, nope, it's not. It's kind of gray. It's fun though. Okay, so here we go. If we can get going, this is not working as fast as I'd like it to. It's thinking, why isn't this going further? I'm a little scared to tap again. Okay, there it goes. I was like, where's my spinning wheel of death? There it is, chapter 2, that's what we're doing. And then we're talking about section 2.1, linear and quadratic functions in modeling. Okay, objectives using polynomials, yeah, right? Okay, functions, use linear functions, use average rate of change, use linear correlation in modeling. That's pretty much what we're going to be looking at today. Tomorrow, Tuesday, we'll talk about quadratic functions and applying quadratic functions. But do you guys remember what a standard form polynomial function looks like? And people are like, yeah, I just pulled that out yesterday because that was something I'm working with. That's what I'm looking for if I just have an example of a polynomial. And I'd have to factor that out. As I pull that out, and remember this is grouping, I'm factoring by grouping. And I pull that out and I get to x squared minus 4. But yet, I can still reduce that because I can factor that still, x plus 2, x minus 2. And I have no idea why it's doing what it's doing to me right now. It's really annoying. But then I got my zeros in my function. And I've got that function all graphed. But what's really cool about this is that we got something in the standard form for a polynomial, and I got an example here. And I know a few things. Coefficients are real numbers, okay? And powers are non-negative integers as we go through. So it's kind of a neat thing to be going, it all makes sense, I hope. Now, let's make sure I'm at the bottom of the page before I slide on. The definition of polynomial function. Let n be a non-negative integer and let a sub 0 or sub naught, a sub 1, a sub 2 to a sub n minus 1, a sub n be real numbers. Remember, those are the coefficients, the leading coefficients in front of each term, okay, or x value. And a sub n is not a zero value. A sub n is not a zero value. The function can be given by f of x equal a sub n x to the nth power plus a sub n minus 1 to x to the n minus 1 power. Okay, and those subs are just the coefficients to go along with each one of the variables. Is a polynomial function to degree n. The leading coefficient is a sub n. Okay, are you okay with that leading coefficient? And I'm trying to tell you the leading coefficient is always the number with the variable with the highest power. Okay. The zero function, f of x equals 0, is a polynomial function. It has no degree and no leading coefficients. Okay. Now, polynomial functions are defined in continuous and all real numbers. Okay. There are no domain restrictions. And people are like, really? We just finished doing those VAs, the holes, removable discontinuities, jump discontinuities, and we don't have those in this chapter. There are no VAs or holes. There are no breaks in the graph. Okay, we kind of did our time with them for a little bit. I'm not saying we're done with them. We'll probably come back and refer back to them. in this chapter. We will talk about them probably a little bit more, but we got to be aware that there are other functions out there that may not have them. Now, is every relation a function? And we kind of done enough work right now that we know that is not true. Okay, so now we got to kind of like think about what makes a function, and you know, and we know the vertical line test. We know if a function's inverse, you know, is a function, we have it one-to-one because it passes the vertical and horizontal line test. Which of the following are polynomial functions here? Okay, now remember, I'm asking you to identify polynomial functions. Polynomial functions, remember the rules above. Refer to them and try to figure out A and B right now. Are they functions or not? Refer to those rules, reread your rules, and using those rules, see if you can determine if A or B are functions, polynomial functions. They could be functions. I'm just asking, are they polynomials? So check out the rules. And I'm looking for functions up there, if I check that out. Has positive powers, got leading coefficients. Okay, I can write it in a, as a polynomial function, a sub n x to the nth power, working down from greatest power to least power with my coefficients. Can I do that in 1? Or I should say A. Can I do it in B? Or can't I? Okay, so I'm looking at A, and I'm talking about A. It kind of fits it. F of x is a polynomial function of degree 3 with leading coefficient of 4. Okay. In B, however, I kind of fail in it being a polynomial function because it has a power of a negative. Okay. As I'm looking at C, I've got to be able to put it in that function form, the polynomial function, and be able to have it be represented as a sub n x to the n plus a sub n minus 1 x to the n minus 1. And I can't put it in there. Okay, h of x is not a polynomial function. It cannot be simplified into the polynomial function form. And my last one, be careful on this one when you look that one over. My last one, you guys try. Okay, takers, anybody want to go out on a limb on this one? Yes or no? Is it a polynomial function or not? I got head shakes. I got head rounds. Do I have powers that are positive? Okay. Can I break it down so I can reorder it if I need to put it in the right form? So I'm really saying, hey, could I do this? Okay, this board is going really slow. Okay, there it goes. We okay so far? I just happen to have x to the third have a leading coefficient of 0, x to the second have a leading coefficient of 0 as well, and I have a leading coefficient here, or I shouldn't say leading coefficient, but a coefficient of 0 of x to the third and x to the second. But a leading coefficient is -2 here, so I'm going to talk about it's a polynomial function, degree 4, leading coefficient -2. Okay, so I mean I can read stuff from it and I can get it done and get it going. Now, all constant functions, as well as the 0 function, are polynomial functions. So the 0 function, f of x equals 0. Okay, it's an undefined degree. The constant function, people are like, what do you mean constant function? Horizontal lines. Okay, constant function. Think horizontal line. Anything that goes straight across the graph. Okay, horizontal lines. Degree 0, constant function. That's polynomial function. Linear functions, okay, of first degree, okay, and quadratic functions, second degree. These are polynomial functions, okay. Now, degree 3 polynomial functions will be studied in section 2.3. This section will focus on the properties and uses of linear and quadratics. Okay, so I've got some people going, why are we talking about the low ones? The higher ones will have their own day. Okay, a linear function is a polynomial function of degree 1 and has the form f of x ax plus b, but keep in mind that's y equals mx plus b, where a and m, that's my slope, constant rate of change. If we use m, the leading coefficient, instead of a, we have y equals mx plus b. Are horizontal lines linear functions? Horizontal lines are not linear functions. They're lines of graphs and they're constant functions. So horizontal lines are polynomials and not linear. Okay, they're a constant function. So they won't be considered linear functions. Are vertical lines linear functions? Think about what a vertical line is. And people say, well, no. But vertical lines are not graphs of functions. Remember, they can't pass that vertical line test because, you know, they're only supposed to pass once. So they fail that vertical line test. Just wonder what I'm doing. I'm taking attendance. Just thought I'd get it done because I have a tendency to forget unless I do it while I'm instructing here. Now, a line in the Cartesian plane is the graph of a linear function if and only if it is a slant line that is neither horizontal nor vertical, because we just talked about what a horizontal line isn't, because it's not linear, and a vertical line, we've talked about as far as that line is concerned. But if I'm looking at this, can you tell what my points are in my function? I mean, what's going on here? I mean, generally I'd give you like, hey, it's a x, y coordinate pair. Have I done that? Remember, generally we have f of x, which is representing y. So I give you x, and I give you y. And I can totally pop over here and talk about, hey, I'm finding the slope of that. And remember, we're finding slope. And I've got to get there. You see, I got that -1 from here and 2. This is x, f of x equals your y, because this is your y value. F of x, when I put x in, and I get out this, that's my y. This is where I got these, okay? So my next thing is get some slope on, okay? And I got the equation for slope up top, and I'm putting it in here, right here. So go ahead and apply your slope as I'm continuing taking attendance. So I've got slope going on here. So I'm going to write an equation. So I've got y equals mx plus b. Do you guys remember point slope form? Okay, vaguely, or yeah. I would use totally point slope form. That's this one right here that I have, right here. That's point slope form. Y minus y1 equals m, x minus x1, times quantity. But keep in mind, When I use this form of the equation, I can solve for y and have it in slope-intercept form, y equals mx plus b form, just solving for y. Okay, so I always start with this. Okay, this is the best one to be using. So as we go through, I've got that going on. And I don't care which point I pull. And people are like, well, it's got to matter. I was like, I don't care which one. You can pull either one of those in for your x and your y value. You're definitely using this for your slope. So when I pop that in there, I decided to pull in the -1, 2, and here's why. It's smaller. I can actually do it on my fingers. I don't have to take off my socks and shoes to do my computations. Thank goodness, right? The olfactory senses would be like affected. Okay, that was kind of a joke. I would use a calculator if I go that high. Okay, are you all right with popping them in? Yes or no? Okay, and recall, remember I got -1 goes in for x. That's subtract the negative, so it's plus, not plus, but plus. And I put 2 in for y, and I get my equation. But now I got to change it over to the function notation, right? So I've got to get that the function notation. So I'm making that conversion. And then my next thing is I'm going to plug it in just to check, to make sure it's going to work. So I'm going to plug in -1 for x. And I get out 2. Hey, that's exactly what it's supposed to be. And I can put in 3 for x. And I'm going to get out positive or -2 as I evaluate. And then they're asking, that's my verifying graphically and confirming numerically. So I've confirmed that it works numerically, but let's verify graphically what it's going to look like. And those same points, -1, 2, -1, 2, and 3, 1, 2, 3, -2, 1, 2, are on my graph. So I've got it set that actually is going to represent what I want it to. So solve algebraically, verify with my numeric numbers being put in to make sure it works, and then what's it look like on my graph, and do the points that I started with actually fit my graph that I made, okay, as I'm going through. Now, I know we did this as algebra students. Most of y'all have that in 8th grade, some 7th grade, okay. I know you did it in geometry, in Chapter 3, Sections 7 and 8. I also know that you did it in Algebra 2 again, and now we're doing it in PreCalc. Okay, just reviewing our linear stuff. Now, average rate of change. It's slope, but here's the deal. Another property that characterizes a linear function is its rate of change. The average rate of change is the function of y equal f of x between x and a, where x is equal to a and x is equal to b. So remember, this is y1, x2. Remember, x goes in, y comes out. I don't know why I put in 2. It should have been 1. y2, x2. Okay, so I'm changing y over the change in x's. I'm just doing slope, okay? And they're just letting it represent as the f of x, for the first one, f of b minus f of a. I've got those 2 points that plugged in. Those are my actual values of y, and b and a are my values of x that went in, and that's how we're showing slope. It's still the same thing we've been doing. Okay, I ain't gonna sing row, 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 this to row, row, row your boat. I want you guys to go, remember row, row, row boat, going through that. Now start singing this to yourself. Okay, if I start singing, it's like cats in a dryer. Okay, it's never good. Okay, so, but just keep in mind, we're talking about slope as we're going through. Constant rate of change, a function defined on all real numbers as a linear function if and only if it has a constant non-zero average rate of change. Okay, non-zero average rate of change between any 2 points on its graph. Remember, horizontal lines are polynomial functions, and we're talking about worrying about constant rate of change, and that's the non-zero was put in there, and we got to remind ourselves horizontal lines are polynomial functions. and average rate of change is just, I'm talking slope. So this happens in a linear function because the average rate of change is constant. This makes the rate of change the slope. Now, and I'm not sure why this is already up. Shouldn't be. It's just suddenly doing some interesting stuff, and it's back. Good. Modeling depreciation with a linear function. Now, and when I model depreciation with a linear function, I'm assuming depreciation is a linear function itself, okay? That there's a constant rate of change every year as I own something. And it's not going to be a percent down. It's actually, I'm going to predict it's going to go down by X amount of dollars. So Camelot Apartments bought a $50,000 building, and for tax purposes are depreciating it $2,000 per year over a 25-year period using straight line depreciation. Okay, and people are like, what did you just say, Bloom? Keep in mind, average rate of change, okay, my initial value of the building is how much? 50 million or 50,000? 1,000, okay. If that's true, I've got a lot more money in my paychecks than was millions, huh? That's pretty cool. All right, just kidding. $50,000, but remember, at time what is it $50,000? Times zero. Does that make sense? And that's kind of a significant piece of information because I'm saying that at time zero, I have my building worth 50,000. 50,000 is my y-intercept. They gave me the constant rate of change, negative 2,000. That's my slope. My slope is negative 2,000. That was my constant depreciation per year is $2,000. So they're asking, what's the rate of change of the value of the building? Well, that rate of change is $2,000 per year. That's what it's going down as. Write an equation for the value V of t of the building, t being time in years, okay, as a linear function, and I just kind of set it up. If we go y equals mx plus b, with m being our constant rate of change of negative 2,000, and our y-intercept value of 50,000, we're able to come up with v of t of that with negative 2,000 t plus 50,000, t being time between 0 and 25 years. So I will be able to put in whatever year it is since I've purchased the building to find out how much it's depreciated, how much is left as far as its cost to me on my sheets for my value assessment. Now, I'm just asking you here in 3, evaluate for year 0 and for year 16. Okay, so you guys evaluate for year 0. We already determined that. What's the value of the building at year 0? You okay with 50,000 because that's our initial time? And then we evaluate for year 16 by plugging it in 2,000 times 16 and making that sum with 50,000. So go ahead and get those done. Evaluate for year 0 and year 16. And then we're going to talk about solve. At what year are we going to have to wait for it to be worth $39,000? How long will that be? Are you okay that year 0 was 50,000, year 16 was 18,000? Okay. And now I can kind of go, okay, year 16, it's now worth $18,000. So the year it's going to be worth 39,000 is somewhere between those two. Okay. Right, between 0 and 16. It's not going to be out on the 25. But when I solve this, I want to make sure I recognize I'm looking at the idea of that I got 39,000 is equal to negative 2,000 t plus 50,000. Okay, 50,000. As I do this, I'm just going to solve for t. I'm going to find out what year it is. Okay, so I subtract 50,000 from 39,000, and I get myself negative 11,000. and I divide, and I got 5.5 is equal to t. Okay. Now, one of the beauties of doing these is being able to explain what our final answer means each time we looked at it. Because we look at 3, we look at 4, we get numbers, but we have to know what we're writing. In 3, we were supposed to evaluate. We're really finding, using straight line depreciation, how much our building is worth at that time. Okay. So in year 0, it's worth 50,000. In year 16, it was worth 18,000, depreciation-wise. In 4, we're finding out that after 5.5 years, okay, our building's worth $39,000. Okay, not only is this part of this is me finding out how to write equations and getting numbers, but being able to explain what it all means. That explanation is a big benefit to you, as you know. And I'm going to make sure that as you go through those, if you've got a word problem, you should have a word answer as we go through these. Now, the rate of change of a linear function is the signed ratio of the corresponding line's rise over run. That is for a linear function. F of x equals, I'm moving stuff all over the place. F of x equals m of mx plus b. Now, here's the deal. This is a chart about what's going on with our table here. And remember, it's a chart with our formula, negative 2,000 x plus 50,000 as we go through. And it's just filling it in, and it's by year, okay? It's our depreciation schedule year by year. And we can continue this chart if we wanted to put it into our calculator, if we so had that need, okay? Now, f of 0 is the initial value of f, okay? That linear, b is the linear, for linear functions, it's the y-intercept, okay? So the constant term, f of 0, is a naught, okay, for our function. It doesn't have a variable with it, okay? For any polynomial function, it's the function's initial value, okay? Whenever I put y0, you know, my x0 in, it should be the initial value of the y-intercept of whatever it is. So where it crosses the y-axis is a significant piece of detail I want to make sure you always have on your graphs when we're testing and when you're doing your assignment. Make sure you put in your y-intercept. And that's all it is when x is 0. Plug it in, get it going, be able to graph it. Okay, characterizing nature of a linear function, verbal, polynomial of degree 1, algebraically it's mx plus b. Graphing, it's a slant line with slope m and y-intercept b. Remember, it's slant line, it's not a horizontal line, it's not a vertical line. Analytics, function with constant rate of change, m, f is increasing if m is greater than 0, decreasing if it's less than 0. The initial value of f of x is, you know, it's equal to f of 0, which is b, the y-intercept. Place where it crosses the y-axis. At this point, you guys have seen this linear correlation data like probably 6 or 7 different times, depending on what classes you've taken. Okay, generally, if I'm looking from left to right, I got a strong positive linear correlation if everything's tight and going in a general left to right positive direction. I want you to think about it this way. If it were my bank account, I would be happy. Right? If left to right going up. Here, this is a weaker correlation, okay? It's not as strong because it's widespread. I mean, I can kind of see an oval look, so I'm of the belief that it's got a weak positive correlation. In this next one, I got very little correlation because it could go up, it could be down. I mean, it just depends on where the data is going. So maybe I can reassess my data or something like that. But then I'm looking at a strong negative correlation and a weak negative correlation. So we have the idea of those, 5 ways I'm going to be able to look at data. Now, correlation strength refers to how well a line fits the data. The direction refers to the slope of the line. Okay, so we've done that stuff. Linear correlation coefficient. I had you set this up on your calculator a couple days ago. I had you do diagnostics on. Did everybody get that done in their calculator? Okay, with the diagnostics on. You got to go in. I've got, check your calculator, go to catalog, then go to diagnostics on, and catalog is in that bottom row. Tim, 0, and then go on and go down the diagnostic on to check that out. And then hit enter, and your calculator will say done. Yep, I'm done. Okay, and you'll know the diagnostics will be on. This is going to help us with finding some correlation data of our whatever we get back when we do a linear regression or a quartic regression or a cubic regression or anything like that. Okay, and we're going to see that next. These properties, you've got something called the correlation coefficient, and that's r to the first power. The correlation coefficient is r to the first power. And you guys saw that when we did that linear example. Okay, so we got a correlation coefficient, and it's going to be between -1 and 1, your r. Okay, now when r is greater than 0, there's a positive linear correlation. Okay, when r is less than 0, it's a negative linear correlation. When I look at the absolute value of r, okay, the closer it is to 1, the stronger the correlation. The closer it is to 0, the weaker the correlation. So you saw an example of what a strong correlation, the data is really tight around my line. Okay, you saw what it looked like as a weak correlation. The data is like all over the place. There's no real trend of the data. Okay, if it's 0, I mean, there's really no correlation. It's a really weak correlation. Yes, you may. You may. Okay, so we got that going on. Good modeling practice demands that we have a theoretical reason for selecting a model. And the models I'm talking about, linear, quadratic, quartic, okay, logistic. We'll be able to pick them. We'll talk about it. Don't stress. But those are all models we can use. And this coefficient correlation will help us out with them. Okay. In business, fixed cost is modeled by a constant function. In economics, demand for a product is a function of its price. And you guys talked about supply and demand curve. You've probably even seen this as social studies. And the sweet spot is the price point, okay, where your supply and demand meet, and you're selling and making a profit, and people are interested in buying whatever you're selling, okay? You'll notice that there is the price is cheaper when you have a lot of products out there on the market, and I want to talk about it as, I'm not even sure if you guys ever noticed. Oh yeah, we do. We have the iPhone X coming out, right? Okay, for you guys, like, it's $1,200, that phone. Okay, people are waiting in line, and they may have to just to order it, and they may have to wait like anywhere from 3 to 6 months to get it. High demand, low supply, big cost. Okay, when the phone's been out in the market for a while, like say, I don't know, an iPhone 5. Okay, the cost of that is like $200. Okay, it's not the new and improved, but it's also saturated the market, and they're just trying to get rid of the things they've had laying around, so they've cut the prices so they can use their supply and be able to use their space to house the new iPhone X. When I was you, it was a VCR. VCRs were like $800. It's hard to believe something that you guys see on the shelves for $20 that is a VCR and a DVD player. Okay, but remember, at the time they came out, there was a high demand and a very small supply, so the prices were very high. And as production continued on and people they started to saturate the market, there are so many now they're just cheap. And I think I've seen some people just using a VCR to hold a door open. Okay, along with the fact, I mean, the tapes. I don't even, do you guys, anybody have a VCR at home still? Okay, I have tapes and stuff, and I got one VCR that'll play them. Okay, but after those tapes are played, I don't think I'll be using that VCR anymore, so I got to switch them over, for the family videos and stuff. So at least we can always have those moments together, okay? But keep in mind, that's how the supply and demand curves work as we go through. Let's talk about Twin Pixie. Makes donut-shaped oat breakfast cereal. They sell 15-ounce boxes at various prices over a period of time. We have a modeling and prediction model, okay? What I want you to do is take your calculator out, and I'll get my calculator here. I've got it hidden back here. And I want you to put these into your L1, L2. Now, y'all might have some stuff sitting in one of your boxes. Let me get something done in one of my boxes. I just want to fill this in with a bunch of junk. Okay? If you have stuff already in a grid and you want to get rid of the grid, this is Bloom showing you a little calculator trick. Instead of going, just arrow up on top of L3, say, in this case. Or actually, I can arrow down at wraps. Okay? So are you okay that I'm on top of list 3? The reason I'm showing this is if your list is full, you can clear it by just hitting clear and then arrowing down and the list clears out, okay? If you hit delete on a list, okay, I'm gonna go over here and hit delete. Oh, that work, it's gone. Go over where you wanna put that list that you just took off, hit insert, second insert, and go back to second L2, because that's the one I wanna put back in, and it's back. And all the stuff that was there, all my data is there, okay? And that's what will happen if I delete a list and my cursor was on top of the list. It just gets it out of the way because sometimes it's better to readjust my list so I can see certain numbers side by side. So it's a benefit to the user of doing it if that happens. But you learn about this trick when you start deleting things and you didn't pay attention where your cursor was and it goes bye-bye, okay? Go ahead and get those in. And we're going to talk about setting it up, and we're going to talk about our linear regression we're going to run on this. That's our last one, right? Oh, you're such a rock star. Thanks for letting me steal. Okay, now, linear regression, but I'm going to load it because I want to see my scatter plot, okay? So I'm going to go into second stat plot. I'm going to turn my plots on. My L1 was my X. Okay, L1's my X. L2 was my Y. I'm good to go. I'm going to go to zoom, and a zoom fit. If I don't have anything else in my calculator, it works. And I don't know why it works sometimes and why it doesn't work other times. So sometimes it works fantastically. Sometimes it totally stinks. And I had something apparently in my graph, and so it took over, and I forgot to take that out. So I'm going to clear this out, and I'm going to go back, and hopefully that I can do 0, and it'll enter in there, and it'll do that again. But it won't, so I've got to look and relook at my numbers again. So I got $2.60, and I've got 29,000, okay, as my Y. So I got to go in my window, and I got to go, hey, I got to go -5 to, I'm going to go 10 for my X's because that's money. My money was X. And then I'm looking at my Y's from 0 to 29,000. So my zoom fit didn't work, and I'm just going to go plop that in. Yeah. Zoom 9, was that the stat plot? Was that the one I was? Yeah, zoom stat should work at. Sorry, I thought that was the one. Thanks for doing that. Zoom 9 will work as well. So now I'm up here and I'm checking this out, and I want to go and do a linear regression model on this. So when I do that, I'm going to go from my second. I'm going to go back to stat. Okay, I want to go to calc, and I want to do a linear regression model. And we did this the other day. So I got a linear regression, AX plus B. I hit enter. And remember, L1, L2, my X was L1, my Y is L2. I'm not going to worry about frequency on my list. I want to store it, though, because I'm going to use it a couple times. I'm going to use the stored data. So I wanted to go to vars. I want to go to Y vars, and I want to be at function. And I'm going to store them in Y1. And I'm going to hit enter. And so that's there. And I'm going to hit calculate. And I hit enter there. Now, when I get this calculate, do you see I got that R, that coefficient? I just found out that it's going to be a negative correlation. My data from left to right is going to go down. But as it's going down, it's not exactly 1, okay? My data, it's not great as far as this graph isn't a really strong correlation, like if it were like 1 or -1 in this case. So just know that as I'm looking that over. But I can store this data in Y1, and I've done that. And to show you that I've stored it in Y1, it's right here in my Y equals list. I put it in Y1, okay? Now, let's look at a few things. Okay, the data I just got. Now, I'm doing this model. We did that in 4, got that. I rounded my model. Don't round your stuff if you can. Use the Y1 area so you can store everything. I checked my R, the strength and direction. I must have put in the wrong thing earlier. I'm questioning my fat fingeritis here. Hold on a second. Because that is not the number I got. Oh, geez, no wonder. Mr. Bloom, you think you're almost done. Good eyes, guys. 3.6. Enter. Whew. Okay, so now that would have been an outlier, so if I included that in my data set, that would make sense. So now I've got this. I go to my calc, I got to do the same thing. I've got to set that all up again. I got my, stat, calc. I want to go to 4. Now 1, 2, vars, there. Oh, here we go, function, y. Okay, now calculate. Happier. I thought it would be better than that. So now I'm up here. I've got that Y1, and I've got the same strength. So I got a strong negative correlation to what I had before. Sorry about screwing that up. But now, remember, I want to run it as price. And I want to show you what you can do for running it through. I could totally put 2 into there and do it. But you guys all have this in Y1, right? So if you put Y1 and put a 2 into Y1, like that, like it's function notation. Okay, back in your calculator. So now I hit second quit. I can go to vars, y vars, function y1, okay, and I put a 2 in there. Because I already have my function stored in y1, it will now do the calculation for me. That is not my calculation. It should come out as units sold here at 42,900. It is my calculation. Okay, 42,900. Sorry, I'm misseeing those decimals. Okay, so that's my calculation with my actual Y1 data, and I didn't round it. Okay, and then I can run 4, because I'm asked to run, hey, what's it look like 4? So I'm going to hit second recall, second entry. I'm going to change the 2 to a 4 when I do that. Maybe, if it'll let me. And then hit enter again. So I just ran the numbers that I have right here. So when I got $4, it's approximately $12,190, and when I do it with $2, I sell $42,900. Now, have you guys seen these folks out in the stores giving you samples? Okay, people give you samples and they'll have a price for the box, but then maybe you really liked it, and over the time you notice that price went from like $1.50 or $2 a box, and it shoots up to like $3.50 to $4 a box. They're trying to find a set point for the price, okay? Because although at first they start giving it away, okay, so that way people get hooked. Hey, this is pretty good stuff for this, like $1. This is awesome. But then they start losing people at a price point set, because as you increase the price, people won't buy it as much, okay? So as we're looking at this, you gotta look at the interpretation. Boxes sold based on the price adjustment, okay, as we're talking about it. So if the price is dropped by $2 per box, demand will rise to $42,900. And that's what we're looking at here, okay, using our model to predict number of boxes sold. Sorry. That's what we're looking at here. If I drop it by $2 a price, you know, $2 per box, if I drop it to 2, it'll increase the number of people who purchase it. But if I raise it to 4, it'll decrease the number of people that purchase it. Okay, as I'm looking this over. And that's my explanation as I'm going through. And then they have a sweet spot with the number of boxes sold, the price per box, and profit made, okay, for profitability of what's going on. And they try to maximize the profit with the number of units sold. Okay, and this section is what I did with the other. So again, example, what I just did. Enter the plot data, find the regression model that fits the problem. We chose a linear. It might be quartic, quadratic, whatever, okay? Superimpose the graph of the regression model in the scatter plot, observe the fit, and use the regression model. We didn't have to observe the fit because we knew it was a strong negative correlation, okay, as we were going through with what's happening. But you guys can look at the superimpose of the graph, okay? That's what I've got for you today. Okay, and thanks Eagle Eye, you know, for finding out where my entry mistake was.